So with our definition of the torque, tau equals Rf, tau equals R cross F, with our new understanding of the cross product, hopefully this makes a little bit more sense, what this means. So just to recap, keep in mind that the cross product, tau, then is going to be perpendicular to R and also perpendicular to F. The cross product always gives us a third vector that's perpendicular to each of the individual ones. Now let's remember, what's the magnitude? Tau equals Rf sine theta. But let's think, have we seen anything with that form other than the torque? Well, let's remember, when we have some mass m at some position vector r moving at a velocity v, what we found was that the angular momentum was r m v perpendicular, or v sine phi. Well, that looks very much like this something something sine phi. We've got something something sine phi. Well, we can make it a little more explicit. mv, what's mv? That's the momentum. So we can write this as L, the angular momentum, is Rp sine phi. So maybe we could define the angular momentum in terms of the vector cross product, R cross P. Maybe that'll work. But keep in mind now, this means that L is going to be perpendicular to R, and in this case, if we again think of something as rotating around like this, with a velocity that way, we might think of it as rotating around this way, which would give us an angular velocity out of the board, which kind of goes along with an angular momentum out of the board. So it kind of fits. However, does the relationship that we thought we had before, where tau was what we had was tau was equal to dl dt, does that work now in terms of our vectors, our new vector definition? Well, let's see. Using L is R cross P. I don't want to really erase that. Let me erase this down here. So does tau equal d by dt of R cross P? Okay, does that still work? Well, what do we get? We get d by dt. Now, we already talked about how to take the derivative of a cross product. That's going to be the derivative of the first, dr dt, crossed into the second, plus the first crossed into the derivative of the second, dp dt. There we go. So what do we get? Well, what is dr dt? Well, that's the velocity. But wait a second, p is the mass times the velocity, so we know that p must be parallel to v. So what is the cross product of two vectors that are parallel? It's 0. So we know that term is going to be 0. And what do we end up with here? Plus r cross, what is dp dt? Oh, well, that's the force. That is the total force acting on the object. And what do we have? Tau vector equals R cross F? Yes, that is true. We know that. That's how we define the torque. So, very good. We still have, with this vector notation, tau is equal to dl dt. Okay, very, very good. I'd like to go over an important point that is very similar to a point that we talked about when we were dealing with forces. The total torque that's acting on a system, we can think of that as R cross the total force that's acting on a system. The total force is, excuse me, R cross the total internal force acting on the system plus the total external torque acting on the system. External force, the sum of all the external forces. Which, taking the cross product of a sum, we can write this as R cross all of the internal forces plus R cross all of the external forces. The R cross the external forces will be the total external torque acting on the system. The torques from all external forces. This term is the total torque from all of the internal forces. Now, what is this? What is the total torque acting on a system due to the internal forces, only the internal forces. Well, let's take a look. Let's pick two objects and look at the interacting forces between them and see what that does to the torque acting on the system. Let's imagine we've got two particles, two objects within our system, say object 1, object 2. Object 2 exerts a force on object 1, we'll call that F12. Object 1 exerts a force on object 2, we'll call that F21. We know that F12 and F21 have to be equal and opposite from Newton's second law. And just for the time being, let's imagine that F12 and F21 act along a line connecting particles 1 and 2. This would certainly be true for gravity. It would also be true of the electrostatic force. So there's a couple examples where this is absolutely true. Let's choose some origin. So here's some origin over here. And the position vector of mass 1 will be this one, R1. The position vector of mass 2 will be this one, R2. So what are the torques acting on each? The internal torque for mass 1, just looking at these two particles, will be R1 cross F12. And then the internal force, the internal torque acting on particle 2 will be R2 cross F21. Okay, so that is the internal torque, the total internal torque for these two particles. If we had other particles, we'd have other pairs of these torques. So as many particles as we have, we just have the pairs between particle 1, particle 2, particle 1, particle 3, particle 1, particle 5, particle 2, particle 3, particle 2, particle 4, etc., etc. Always coming in pairs with the opposite forces. Now, let's change F21 into a negative F12 because we know they are equal and opposite. I'm going to change this to F12 and make this a negative. Okay? Now, we've got the same force here, so rather than the distributive law where we're separating things, we're going to factor this out. So this will be R1 minus R2 crossed into F12. What is R1 minus R2? Well, that's a vector. Remember, when we subtract vectors, what do we get? That's going to be a vector that points, if the two vectors are tail to tail, which R1 and R2 are because they are both coming from the origin, the difference of the two vectors will be a vector that goes from the point of R2 to the point of R1. In other words, R1 minus R2 will be a vector that looks like that. So this is R1 minus R2. A vector from the tip of R2 to the tip of R1. But what do we notice? This vector it's either anti-parallel to F12 or parallel to F21, which means when we take the cross product of R1 minus R2 with either F12 or F21, what do we get? We get 0. So we know that this must equal 0. And that's going to be true for any pairs of particles as long as we said, the forces, the interacting forces are along a line between them. So at least for those forces, the total torque due to the internal forces has to be 0. So what do we have? We have that the total torque acting on a system is only due to the external forces. The internal forces cannot create a torque on the system itself. Very, very good. Let's look at one system with a very interesting relationship between its torque and its angular momentum. As an example, I would like to look at a gyroscope. Now, what is a gyroscope? It's like a spinning top. So here I have a wheel, and what I'm going to do is I'm going to give it some angular momentum by spinning it this way in a positive direction. So assuming that this is the axis pointing towards you, positive is counterclockwise, so I'm going to spin it that way. And then what I'm going to do is I'm going to support it by the back here, at this back end. And I'm going to do that by taking a piece of rope and attaching it to the wheel and holding the wheel up like this. And that's the only way I'm going to support the wheel. I'm going to let go with my hand. And let's see what happens. So let's give this a go. So pointing towards you, positive rotation this way. Okay. There. Now I'm going to take this, I'm going to put it on the back here, and now I'm going to let go. It rotates around. And it's rotating around. When it's pointing towards you, it's going that way. So let's take a look at that. What is going on here? So here we go. Here's our wheel, our gyroscope. It's spinning this way, all right, in a counterclockwise direction. So we know that the angular velocity this way, which gives us an angular momentum pointing out of the board. So L is going to point out of the board this way. Looking at it from the side, L then points that way. If we look at it from this direction, here it's rotating this way, and we look at it from the side here, the front is moving towards us and then down this way. So the rotation is in this direction. The angular momentum will be that way. Now let's figure out what's going to happen to this angular momentum due to the forces acting on it. So what forces are acting on the gyroscope? Well, there's the gravitational force acting on the gyroscope, pulling straight down. So this is the weight of the gyroscope. There's also a tension acting in the rope. So those are the forces, the weight and the tension. In order to determine the torque, we need an R vector, which is a vector from the origin to the point where the force is applied. So we need to define an origin. Well, let's define the point where the rope is attached. That's the origin. Okay, so what is R for the weight? R will be a vector that goes from the origin to the point where the force is applied, which is at the center of the gyroscope. So that's R. What about R for the tension? Well, the tension is acting right at the origin, so R is 0. The tension has a position vector, R, 0. So what is the total torque? What total torque do we have? The total torque will be equal to R cross the tension, so R for the tension cross the tension, plus R for the weight crossed into the weight. But R for the tension is 0, so 0 cross the tension is 0. The tension is going to give rise to 0 torque. There's no tension due to the torque. Due to the tension, sorry. What did I just say? There's no torque due to the tension. What is the torque due to the weight? Well, that's going to be the distance, RW. What's that distance? Let's call this some distance D. The distance from the point where we attach the rope to the center of the gyroscope. So that's some distance D. D times the force, RF, so times the weight, times the sine of the angle between them. Now what is phi? What is phi in this case? Well, here's R, here's the weight. R is horizontal, assuming we have the gyroscope starting out horizontally. The weight is down. What's the phi? 90 degrees. Sine of 90 is 1. So there's the torque. Now what's the direction of the torque? Well, let's bring the weight over here, or we'll bring R over there, either one, bring the weight over here. Okay, there we go, there's the weight. We have to take R cross F. So remember, torque is equal to, well, R cross W. We've got it written there, so that's good enough. So how do we do that? How do we find the cross product? Remember, 1, 2, 3. So R, F, down. My thumb points into the board. So this cross product will be into the board. In other words, the way we were talking about it before, in the negative z direction. So dw negative z hat. there we go. There's the torque, negative dwz hat. And that is going to be dl dt. But L is pointing that way. So dl dt is going to do what? Well, let's imagine we look down. We look down from this, and what do we see? Well, we see this is rotating around. The angular momentum is this way. It's supported over here. But now we're looking from above. This is L. dl is into the board, which would be if we're looking up from here, it would be to the left or up here, left if I'm facing it this way. So dl is this way, which means L is going to rotate that way. L is going to rotate into the board. And that is exactly what we just saw. When we start this rotating, L, which started out this way, rotates that way, in this way, around from above, looking in a counterclockwise direction. Let's try that once more. I've got to be a little bit careful. I kind of sprained my finger when I rotated it the first time. Okay, there we go. Going to attach the rope, and what do we notice? It rotates. When it's pointing towards you, it goes that way. And then the torque is always constantly going to be perpendicular to L, and so because the force is always perpendicular to the weight, and it just keeps going around until there's enough friction that it finally kind of drops down and stops its rotating. Very, very interesting. Back to our drawing from above, we have this angular momentum this way that is then moving this way because of the torque that we have. And let's look at this. So over some time, say dt, some time dt, let's imagine that our angular momentum changes by an amount dl. What we have is, if this is a rotation through some angle, we'll call that d theta. What we know is that dl equals L d theta, or d theta equals dl over L. Now let's divide by delta t, both sides by delta t. D theta over dt equals dl over L dt. D theta dt, what is that? That is omega. That is the angular velocity at which this angular momentum is rotating around. So how rapidly is that gyroscope rotating around? So I'll write this as omega. And omega equals dl over dt. But what is dl over dt? dl over dt, that's the magnitude of the torque. That's d times w, or d times mg. So that is d mg over L, the angular momentum. There we go. This is called the angular velocity of precession. Whoops. The angular velocity of precession. Yep. Spelled it right. Wanted to make sure there was two S's in there. And what does that tell us? It tells us how rapidly the gyroscope, as the gyroscope is spinning, and I'll just kind of hold it this time, as the gyroscope is spinning, how rapidly does it rotate around this way? What is omega of this rotation? Not omega for the wheel itself, or the gyroscope itself, but how fast it's precessing. The precession is not the rotation motion, but it's the motion of the rotation rotating around. So we've got two different kinds of rotation. Very, very good. Okay, what we're going to do next time is take a look at how forces and torques can be applied to solve a different kind of set of problems, problems where there is no motion. And when there is no motion, we must have no force or no net force acting on the system. And likewise, if it's not rotating, if it's not moving, it's not rotating, no net torque acting on the system. We'll take a look at that next time. See you then.